In this section of the transmission system tutorial, we will explain the steps required for performing small signal stability analysis, which is defined in Powerfactory as modal analysis. To start, please activate from the project overview window study case number 4 named small signal. In general, the steps we need to perform are the following: calculate a load flow, calculate initial conditions, and execute the modal analysis. If we don't have a valid load flow solution, meaning if we don't have convergence, for instance, or if we have a model error because of a missing type of an element, we will not, of course, be able to continue with the procedure. So we calculate first of all a load flow by clicking on the Calculate Load Flow button. The settings are here important also for the starting point of the simulation, or in this case for the execution of the modal analysis. So we will leave the current defined settings, which are considered reactive power limits of machines, and in the active power control as dispatched by reference machine. Once we have calculated a valid load flow, we can proceed with a modal analysis simulation. First, make sure that you have the correct toolbar selection, which should be selected as modal analysis. A group of buttons will appear related to this functionality. The next step would be to click on the Calculate Initial Conditions button. In the command dialog, we will select the simulation method RMS values and network representation as balanced, positive sequence. We will click on Execute. Once the initial conditions are calculated, we can execute the modal analysis. The modal analysis calculates the eigenvalues and eigenvectors of a dynamic multi-machine system, including, of course, all controllers and power plant models. The calculation of eigenvalues and eigenvectors is the most powerful tool for oscillatory stability studies. In a multi-generator system, for example, we can say that it exhibits oscillatory stability if all complex conjugate eigenvalues that make up the rotor oscillations have negative real parts. That means that they are damped. As a general note, we can mention that the computation time for the modal analysis is approximately proportional to the number of state variables to the power of 3. In very large systems, for example, the computation of the entire system modes would be very time consuming and impractical. This is the reason for Powerfactory to have two different calculation methods. One is defined as a QR method, and the other one is the selective modal analysis, which is also named Arnoldi-Lanczos method, which calculates only the modes of interest. In this example, instead of calculating all system modes, we will use the Arnoldi-Lanczos method that will reduce the computation to only the modes of interest. Let's suppose in this example that we want to calculate the select eigenvalues according to a dominant mode of 1 Hz. The imaginary part there stated in Powerfactory is here given in radians per second. So translated, this 1 Hz in radian per second would be 1 times 2 times pi, which gives us 6.28. We need to then define which eigenvalues we want to calculate. So there are 3 possibilities. One is smallest magnitude with respect to reference point, which defines a circle zone. The other one is smallest imaginary part with respect to reference point, which gives us a constant zone definition on the y-axis, and smallest real part with respect to reference point, which gives us then definition in the x-axis. So we can set also the number of eigenvalues to calculate. In the Advanced Options tab page, we can select also to calculate left eigenvector, which is the controllability information, right eigenvector, the observability information, and also the participation factors. We click then on Execute. The modal analysis is then performed, and then we can proceed on the plotting of results. To plot the results, we will need to go to the Select Plot Type button, and from there we have 3 possibilities: mode phasor plot, mode bar plot, and eigenvalue plot. If we select the eigenvalue plot, Then an eigenvalue plot is created. The definition here in this eigenvalue plot is if it's a stable eigenvalue, it's indicated as a green X. If one of the modes results unstable, meaning that it has a positive real part, then it will be then indicated as red. In this case, we can see that the modes associated are all stable. Powerfactory has also the option of generating a tabular format of results. This can be achieved by clicking on the results of modal analysis button. If we then click on execute, then Powerfactory gives a list of all the calculating modes, 1 to 8 in this case, and it gives the corresponding information for the real part, the imaginary part, the magnitude, the angle, that is, the first two columns represent the rectangular definition. The third and fourth column represent then the polar for definition. You have also additionally a damped frequency information that is in hertz, the period, the damping ratio, the damping time constant, and the ratio between two consecutive peaks, which is the ratio between A1 and A2. From this list, it is very easy to see if the system is stable from the small signal stability point of view. The real part of all the modes then should be negative. The participation factors of each mode can be obtained also from this list by selecting the corresponding mode, right mouse button, show, bar plot, and we can select participation. Powerfactory then creates the mode bar plot, indicating the participation factors. In the eigenvalue plot, if you double click on one of the modes, then you get also the same information that was obtained in the tabular form. You can also, from this eigenvalue plot, select the mode, right mouse button, create bar plot, or create phasor plot. Let's say participation, and then the corresponding plot is generated. We can very easily also repeat the same type of analysis, but considering other scenarios, for instance, such as high load, low load operation scenarios, or considering a different system topology. For example, if we reset the calculation and then take one of the transmission lines, specifically maybe one of the 225 transmission lines out of service, by right-clicking on the corresponding line and then simply selecting switch off, and then repeating again the same procedure. So we said low flow calculation, we calculate initial conditions, we calculate eigenvalues with the same selective modal analysis option, and then we plot again the results. This will give us then the new corresponding modes for this particular configuration of the system. We can also generate the table format and analyze the results. For more detailed information on Powerfactory's modal analysis module, please refer to the user's manual. The user's manual can be easily accessed from Powerfactory by going to Help, clicking on User's Manual, and from the document going to Power System Analysis Functions and to the Modal Analysis Eigenvalue Calculation. There you will find detailed information on the introduction, theory of modal analysis, how to complete modal analysis, and troubleshooting.